Okay, today we are going to discuss a topic. Kari topic no having matamda method of Lagrange multiplier. Lagrange multiplier. Say this method is due to Lagrange, and this method is called the method of Lagrange multiplier. Natraga Lagrange method of undetermined multiplier. Okay. So Sigi method we have a function f of. We have a function f which depends upon many variables, n number of variables, x1, x2, dot, xn. This function this f is a function of n variables. Aduga, we want to find the extremum of this function. Extremum of this function, it can be either minima or maxima. Sigi function minimum to ABI, maximum value to ABI. We want to find the extrema of this function subject to some auxiliary condition. Sigi functions the variable x1, x2, x3, and so on till xn. This n number of variables, they satisfy some auxiliary condition. When a condition satisfied, let us call it g, x1, x2, and so on till xn. They satisfy some auxiliary condition which is given by g equal to some constant. They satisfy this condition. Let us write equation number 1. Aduna, a function number functions the variable x1, x2, and so on till xn. We have independent oide. ID this variables x1, x2, x3, and so on till xn, they satisfy a constraint equation. The constraint equation to g equal to some constant. Find the extremum value of this function subject to this constraint. And you can find the extremum value of this function where the variables x1, x2, x3, where the variable x variables, they satisfy this constraint. See, constraint is satisfied x satisfied to matamda see function extremum value to put over. Third is the important point. See, if f of x1, x2, and so on till xn is an extremum. It's an extremum at some point. At some point, say, let us call it P. P magi coordinates is x1 0, x2 0, and so on till xn 0. Let this function be an extremum at some point P, whose coordinates are given by this. Then df and df, which is equal to del f by del x1 dx1 plus del f by del x2 dx2 plus and so on till del f by del xn dxn equal to 0. Sigi function extremum value say sigi points the then this total differential of f is 0 at the point, at that point. It's 0. So df, I repeat, if f is an extremum at some point P, whose coordinates are given by this, then the total differential of f is 0 at that point. P have a point to the total differential is 0 again. Constraint first, let me call it question number 2. If there were no constraint, constraint equations constraint equations if there were no constraints, then all these variables x1, x2, x3, and so on till xn, they would be independent. They would be independent. Constraint equations variable x, they would be independent. Independent. This condition, the total differential equal to 0 at that point, mana condition bigani, mana conditions del f by del x 1 equal to 0, comma del f by del x2 equal to 0, and so on. Del f by del xn equal to 0. Karigumba constraint equation Karigumba constraint equation sigi variable x map independent independent total differential 0 tawa each of this coefficients of dx1 coefficient, dx2 coefficient, and so on till dxn coefficient, all these coefficients would be 0. If all the x are independent, then all these coefficients would be 0. Coefficient 0 tane. However, constraint constraint x independent 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 0 tani. Some of them can be 0, but we cannot claim that all of them are 0. All of them are 0. Some of them can be 0. So, aduna constraint equations yaw targadi extremum conditions now this condition will not be a condition for the extremum condition. Function extremum conditions. Why? Because of the presence of this constraint. Because of the presence of this constraint, all the x's, they are not independent of each other. We use the method of Lagrange multiplier. Lagrange multiplier method. What should we do? First, we take the total differential of g. First, let us take the total differential of g. So, dg is equal to z. Z depends on x from x1 to xn. So, dg will be del g by del x1 dx1 plus del g by del x2 dx2 and so on till del g by del xn dxn. And since the right hand side is a constant, the total differential of this should be equal to 0. So this is equal to 0. Let us call this question number 3. Lagrange method of multiplier. Method of Lagrange multipliers to the the total differential of g. We multiply this total differential of g by a parameter. Parameter lambda, and we subtract that result from equation number 2. So I repeat, in the method of Lagrange multiplier, what do? We multiply the total differential of g by a parameter lambda and subtract the result from equation number 2. And what do we get? We get the following result. So let me explain it here. So we multiply this equation by lambda and we subtract from this equation. So what do we get? So the yengo adu itari equation pangadrisi kaino del f. So the del f by del x1 angani del f by del x1. Similar. Ko adu lagi minus lambda times this minus lambda times del g by del x1. So now so this is dx1, so this is dx1, and then so this is dx1. So when we subtract lambda times equation number 3 from equation number 2, what do we get? Sidagi lambda times this one the first term I get this x1 plus sidagi lambda times this one del f by del x2 minus lambda times del g by del x2 times dx2 plus and so on till last term this minus lambda times this del f by del xn del f by del xn minus lambda times del g by del xn. There you go. Multiplied by dxn. So there this minus lambda times this need, and since the right hand side is 0, this is 0 minus lambda times 0, which is again 0. So this is equal to 0. So in the method of Lagrange multiplier, this is the equation that we obtain. So as we have said, x1, x2, x3, and so on till xn, they are not independent of each other. Why? Because of this constraint equation. So constraint equation number of independent variables, they will reduce from n to n minus 1. See constraint equations. This equation of constraint, the number of independent variables n never. See constraint equations number of independent variables how many independent variables will be there? There will be n minus 1 independent variable. So n minus 1 independent orani aduga amana dependent dependent orani. Let us choose that this variable xn is dependent variable to choose Taurus. Let xn be the dependent variable. Xn depends upon all other variables. We have chosen xn to be the dependent variable. Xn depends upon all other variables x1 to xn minus 1. That means this differential xn dxn also depends upon all other differentials dx1, dx2, dx3, and so on till dxn. Clever choice by a clever choice of lambda, we can make this coefficient of dxn 0. So 0 manan be I think equation number 3 is lambda ko parameter amna puri salaga equation number 2 the kaido and what did we obtain? We obtained this equation. Lambda can be any parameter which we choose. Clever choice we choose lambda in such a way that the xn dependent variable coefficient is 0. So we choose our lambda in such a way that this coefficient is 0. That is so we choose lambda choose lambda to eliminate, eliminate the
Sir,
term.
could you get the slow track?
Okay. In dxn. This is the one. So from equation number 2, we have subtracted lambda times equation number 3, and we have obtained this equation. And I repeat, since there is a constraint equation, the n variables x1 to xn, they are not independent. Constraint equation amalai banina, masagi independent variable mayam dudagi machine independent over machine amahandarani. That means one of the variables will depend upon the remaining n minus 1 variables. Adagi dependent variable to xn lorasi. Let us take this xn to be the dependent variable. This xn can be expressed as functions of x1 to xn minus 1. Now we choose our lambda in such a way that this coefficient of dxn, in such a way that this coefficient is 0. To choose the way go by a proper choice of lambda, we can eliminate this term. So let us call this question number 4 first. Question number 4 question number 4 gi dxn terms. Dxn terms 0 0 by choosing the coefficient of dxn to be 0. Stay there. We choose our lambda to eliminate the term in dxn. I repeat, we choose lambda to eliminate the term in dxn in equation 4. By choosing that del f by del xn minus lambda times del z by del xn equal to 0 at the extreme. Shiniko, at the extremum, we choose our lambda in such a way that this is equal to 0. This is equal to 0. In equation number 4, in this equation number 4, this term is 0. This term is 0. Now this summation will go from dx1 to dx n minus 1. So there will be n minus 1 differentials. Since x1, x2, x3 till xn, they are all independent of each other. So you can n minus 1 value, n minus 1 variables to the machine independent or banina. Sisu 0 sakramina, siaroi. Aduna, I have Kaitani, 0 sakitari, equation number 4. Kaitani, equation 4 reduces to equation 4 to Kaitatani has been del fy del x1 minus lambda del z by del x1 dx1 plus del f by del x2 minus lambda del z by del x2 and so on till del f by del x n minus 1 minus lambda del z by del x n minus 1 dx n minus 1. This is equal to 0. So the dx2 what let me write it here, dx2. Now in this she said dx n minus 1 because we have chosen lambda in such a way that this is equal to 0 at the extremum. Therefore at the extremum dx n term so at the extremum this is the equation. And now since dx1 dx2 until dxn, the dxn minus 1, this is n minus 1. If it is not clearly visible, this is dxn minus 1. Since all these dx, they are independent of each other, what do we get? Since they are all independent of each other, what do we get? We get that their coefficient should be 0. Coefficient by 0 with them now. all their coefficients should be 0. That means del f by del x I, right, minus lambda del g by del x I equal to 0 for I from 1 to till n minus 1. Because all this dxi, dx1, dx2 till dx n minus 1, they are independent. Therefore, independent coefficient position sum 0 all their coefficients should be 0. So let us call this equation number 6 and let us call this equation number 5. So when we combine equation number 5 and 6, what do we get? We get, so let us combine, combining equations 5 and 6, we get del f by del xi minus lambda times del g by del xi equal to 0 for I going from 1, 2 and so on till n minus 1. So n minus 1 ki le n ki le I goes from 1, 2 till n. We call it equation number 7. Yarba. Thus, final results. So I can go from 1 to n. So this in total equation machine cannot. These are n number of equations. These are n number of equations starting from I equal to 1 to I equal to n. Starting from I equal to 1 to I equal to n. These are n number of equations. So you have n number of equations here. N number of independent variables, n number of variables, x1, x2, x3, x4 till xn. And then we have one more unknown parameter, lambda. So we have n number of equations here, but we have n plus 1 unknowns. N plus 1 unknowns, n number of equations uniquely determine the way n number of unknowns uniquely determine the way we require n plus 1 number of unknowns uniquely determine the way we require n plus 1 equations. N plus 1 unknowns n plus 1 unknown the x1, x2, x3 till xn and lambda. So we have n plus 1 unknowns. And to determine this n plus 1 unknowns uniquely, we need n plus 1 number of equations. Equations for I from 1 to n, we already have n number of equations. So we need one more equation to determine all the unknowns uniquely. One more equation, that one more equation will be equation number 1. Using equation number 1 and equation number 7, we can uniquely determine the values of the n plus 1 unknowns at the extremum value of f. Method of Lagrange multipliers. Method of Lagrange multipliers function of pyramid, equation of constraint pyramid, function extremum value at the extremum value of the function f and g should satisfy these conditions, n number of conditions. So combining this n number of equations with equation number 1, we can uniquely determine the values of x1 to xn and lambda at the extremum. So let us consider one example. Let us consider one example. And that example is given by this. Can you see this? That example is this. Question example number 1. Find the maximum volume. Find the maximum volume of the cuboid whose total surface area is capital A, using the method of Lagrange multipliers. Find the maximum volume of the cuboid whose total surface area is A, using the method of Lagrange multiplier. Adudi cuboid to sine lor se ba. Cuboid ki edge amasi origin de lere. One edge is set of origin. One face cuts the x-axis at x, another face cuts the y-axis at y, and another face cuts the z-axis at z. Then the volume of this cuboid will be given by x, v equal to x times y times z. This is the volume. This is the volume of the cuboid. And what is the given condition? The given condition is that the total surface area is a constant. A is a constant. A is a total surface area. So a cuboid has 6 faces. Cuboid is face taruk lay. Face taruk lay taruk maxi loinamok determined away the galite because opposite this face and this face. Opposite faces are equal in area. So face ahum khak manadaba face ahum khak manadaba face ahum khak determine total area. So this face, the area of this face is given by xy. Therefore, the area of this upper face will also be given by xy. So xy. The area of this face, the area of this face. So we face it. The area of this face is given by yz. And the area of this face is given by zx. Aduna 2 times area of x, 2 times xy plus 2 times yz plus 2 times zx is equal to a. That means xy plus yz plus zx equal to a by 2. So we have the function v, which is given by v equal to xyz, and we have to extremize this function subject to the condition that xy plus yz plus zx is equal to a by 2. This we call g. Extremize this function subject to this condition. Method of Lagrange multiplier VGF del f by del xi minus lambda times del g by del xi should be equal to 0 for values of I from 1 to n. Here we have only 3 variables, x, y, and z. We have only 3 variables, x, y, and z. Therefore, I goes from 1 to 3. So first, you differentiate f with respect to x. So del v by del x. What is v? V is xyz. V is xyz. So del v by del x minus lambda times del g by del x. So first you take xi equal to x. Then you take xi equal to y. Then you take xi equal to z. So first let us consider del v by del x equal to minus lambda times del g by del x. So del v by del x, what is v? V is xyz. So if I differentiate v with partially with respect to x, what will we get? We get yz. So we get yz here. Minus lambda times del g by del x. What is g? G is given by this. So if you differentiate this partially with respect to x, what will you get? You get y plus z. Y plus z. So del g by del x is y plus z. So we have minus lambda times y plus z. Next time we go. Next With this, we differentiate v with respect to y again. So v is xyz. So xyz partial differentiation with respect to y will give you xz, and del g by del y, del g by del y. If you differentiate this partially with respect to y, what will you get? X plus z. So x plus z. Del v by del z, del v by del z is xy, and minus lambda times del v by del z. So this is not v, this is z. This should be z. Del z by del z. When you differentiate this with respect to z, what will you get? Y plus x. So x plus y. Equal to 0. 0 so yz minus lambda times y plus z equal to 0. Xz minus lambda times x plus z equal to 0. Xy minus lambda times x plus y equal to 0. So this gives we take this lambda y plus z to the right hand side, you get yz equal to this. Similarly, xz equal to lambda z plus x plus z. Xy equal to lambda x plus y. And then 6z right hand side because I want to solve x, y, and z. So you call this equation number. So equation number 1 koro, so 2 koro, 3 koro. This equal to equation number 3, 4, 5. So if I divide equation number 3 by equation number 4, if I divide this equation by equation number 4, what do you get? I get this. So if I divide equation number 3 by 4, I get the left hand side is yz divided by xz. The right hand side is lambda y plus z divided by lambda x plus z. So z will cancel out. We get y by x on the left hand side. This lambda will cancel out. We get y plus z by x plus z. Then you cross multiply Toro. So we get xy plus yz. Xy plus yz equal to xy plus xz. So this xy and this xy, it cancels out. What do we get? Yz equal to xz. Z cancel. So without it, what do you get? Y equal to z. Sorry, y equal to x. So from these three equations, equation number 3, equation number 4, equation number 5, equation you can easily solve x, y, and z. And you find that from equation number 3 and 4, you find that y equal to x. Similarly, you can also find that y is equal to z. Hence, it means x is equal to y is equal to z. Now we substitute this. We substitute this in the equation of constraints. We substitute this in equation number 2. So the x to y to z to money this is x square. This is also x square. This is also x square. So 3 times x square equal to a by 2. So 3 times x square equal to a by 2. This means x square equal to a by 6, which means x equal to root over a by 6. So x to y to z to the cuboid with all the 3 sides equal means it is a cube. Therefore, the shape is a cube, and its volume is given by cube amagi volume side amagi cube. So it is cube of this. Cube of this is a by 6 to the power 3 by 2. So this is how we use the method of Lagrange multiplier to extremize a function. Can I call? Okay. Good.